Thank you very much for the introduction. Thank you all for coming. And thank you especially, Jean-Paul, for the kind invitation. I'm very happy to be here. So I'm going to present joint work with Balthazar Boer, Puya Farshim, and Adam O'Neill. As mentioned, the paper that this talk is based on was published at last year's TCC. My plan for this talk is to not dive into the main topic straight away, but to rather give you an introduction, so slowly set the background, and so that hopefully once all the pieces are in place, it will be clear what was the problem that we were trying to solve and sort of where we were coming from. I do have material for around 45 minutes, but feel free to interrupt me at any time. I'm happy to leave a few things out in favor of discussions or questions or new theorems. I don't know. So I want to start at the very beginning of theoretical cryptography, which is the provable security approach to theoretical crypto. The provable security approach rests on two main pillars. The first one is to provide formal definitions of the constructions that we want to prove secure, of the type of security that these constructions achieve, and of the threat model, of the adversarial capabilities that these constructions must resist against. And then the second point is to give rigorous mathematical proofs of the security that the schemes we have defined indeed achieve the security that we want. So if you adopt these two pillars, statements about the security of schemes take the form of mathematical theorems. For example, you could formulate a theorem like this: that the one-time pad is perfectly find then guess under no message attack secure. And notice that for this theorem to make sense, you got to define what the OTP is, which is the bubble here on the left. You must define the FDG NMA game, which is the bubble on the right. And then once you have these two things in place, you can give the formal proof that this holds. Now, if you restrict yourself only to these two principles, unfortunately, you're not going to get very far. There's not many constructions that we can prove secure only out of these two. And what we can prove secure, for example, this, often falls short of what we actually need. The reason for that is that we are currently unable to prove unconditional lower bounds in complexity theory. And so what one usually does is one adds a third pillar to the previous two, which is to state any unproven assumptions necessary for our proofs to go through. These assumptions may come from complexity theory. So for example, P not equal to NP, or the stronger NP not included in BPP. It may be the existence of cryptographic objects. So for example, one-way functions, PGGs, there's many more. It may be hardness of certain mathematical problems, factoring, D-log, learning with errors, and so on and so forth. And if you do that, then well, the community can study these problems and see if they are indeed hard. We can increase confidence in them. So the community working on these problems, this increases the confidence that these problems are hard. Or otherwise, by studying them, you might actually break them. So for example, in light of recent progress, basing the security of a scheme on the SIDH problem might not be such a good idea. Now, if you adopt also this third pillar over here, the landscape of schemes that you actually can prove secure is much richer. For example, you can prove something like this. Let's assume that pure Fs exist. Then you can prove that CPA secure symmetric key encryption exists. And again, as before, you got to define the game. You got to define your candidate construction. And once you have these two things, you can formally prove that this scheme achieves that form of security. OK, so with three pillars, again, the number of schemes that we can prove secure is much larger. But still, sometimes just making assumptions, non-tautological assumptions, falls short of allowing us to prove constructions secure that we somehow deem natural. And my favorite example of this is the Fiat-Shamir transform. So very briefly, I'm just going to explain how this works. So suppose you have an interactive protocol between two parties, prover and verifier. The prover wants to convince the verifier that he knows a witness to the statement X, so witness W to statement X. And assume that the protocol is public coin, which means that the messages the verifier sends to the prover are just random bits. Well, intuitively then, it should be possible to make this protocol non-interactive using a hash function. How? Well, the prover would simply, like prover and verifier, agree on a hash function to use, here symbolized by the hash key. And then the prover runs the protocol in his head and replaces the adversarial messages with hash function evaluations. And intuitively, this is secure because if you have a good hash function, then this returns random looking outputs, even though they are computed deterministically. And so in some sense, this replicates what the verifier did in the previous slide. And here, the verifier would just send random stuff. So if you wanted to make this, this intuition formal, the question you have to answer is, for which protocols pi and hash function families h is this transform protocol sound? And unfortunately, our understanding of this question is quite poor. There are only a few results, a few scattered results out there, but we are far away from a complete picture of understanding when this actually is secure, which is a bit of a bummer. But if you somehow still wanted to validate this design of a protocol, you have to look somewhere else. Problem is, we don't even quite know what assumptions on H we could make for a proof here to go through, other than tautological ones. We can always ask, yeah, well, let's assume we have an H such that this is secure. This is tautological and not very interesting. So if you still wanted to validate this design, one option is to go in a so-called, to study this protocol in a so-called idealized model. This means the following. So we take the protocol and we replace some component by an ideal object that this component is meant to implement. So we would do this here for the hash function, for example. But there are, like, in general, there are many more possibilities. You could replace a permutation, or you could replace a block cipher, or an underlying group, maybe. So there's many possibilities. Again, here we would replace the hash function by a so-called random oracle. And so this here is what you see here. This is the same protocol as before, but where the challenges are computed now with random oracle evaluations rather than hash function evaluations. And it turns out that in this setting here, you can actually prove a very nice result about the security of this protocol. For example, it is a folklore result that if your protocol is constant round, public coined, and computationally sound, then this transform protocol in the random oracle model is also computationally sound. So I hope I could convince you to some extent that ideal models are powerful. They have many advantages, and I'll tell you a bit more about those, but they come with their fair share of controversies. So on the side of the advantages, they make proofs tractable. So working in an idealized model allows you to formally prove the security of a protocol, which is closely related to a real-world protocol that you're really interested in. And then you might argue that knowing the security of a related protocol is better than having no proof at all. Idealized models often serve as guides towards efficient protocol design. So it often happens that if you design a protocol with an ideal model proof in mind, the result will be more efficient than a standard model counterpart, because then a protocol that wants to be secure without appealing to an idealized model, because then you have to often you have to use certain tricks or certain components that lead to less efficient designs. Idealized models provide reusable proofs because they are independent of the concrete object that will instantiate them. So say you prove a protocol secure in the random oracle model. If you believe in the random oracle methodology, then the instantiation of the random oracle with SHA-256 or SHA-3 or Shake, they will all be secure if you believe in the random oracle heuristic. Constructions in idealized models often achieve the best possible bounds. So it often happens that you prove a construction secure in an idealized model, you get a bound, and then you have a matching attack that is almost as good, maybe up to a small multiplicative constant, is almost as good as the bound that you have proved. But above all of these, idealized models just seem to work. So we have no example of a scheme that is secure in an idealized model, but broken in practice. The only way where we can break this in practice is if we instantiate the ideal primitive with an insecure instantiation. For example, if you instantiate a random oracle with MD5, well, then the result will probably not be secure. I mentioned there are also a few downsides. There's mainly one, which is idealized models are not sound in general. So we know that there exist protocols that you can prove secure in an idealized model, but are provably secure under any possible instantiation. And this is the celebrated result in this regard. So you can prove, for example, the existence of an unforgeable signature scheme in the random oracle model, such that whatever hash function family you take to instantiate that random oracle, the resulting scheme will be insecure. So again, this is a bit of a bummer. I mean, idealized models are very powerful, but we know that there are these, they are artificial, but still there are these counterexamples. The question again is what to do about this. And over the years, researchers have suggested a number of approaches to deal with this problem. The one that is important for us today is summarized by this question here. So the question is, can we define a property on the concrete object that is supposed to instantiate the idealized model, be it a concrete hash function, a concrete block cipher, a concrete group, with two properties? So it must be standard model. It must in particular avoid the impossibility results like the one that we have seen before. And then it should allow to instantiate the corresponding ideal component, say the random oracle, an ideal cipher, a generic group, in many applications of concrete interest. Because if you can do this, then we can, with all those constructions that just use the ideal primitive, we can replace it. We can replace the ideal primitive by a standard model object that satisfies this assumption, which does not suffer from the impossibility result, but still gives you the interesting applications that you're after. Okay, so this question has been studied for a few idealized models. I will now show you how the solution for one of them, chronologically the first one, the random oracle model, because this actually is the source of inspiration for what I will talk about later. So, okay, so remember what we're after is a notion for concrete hash functions that avoids the impossibility result of Canetti-Goldreich-Halevi, but allows to instantiate the random oracle in many interesting applications. So the starting point, this has been done in a paper, in the UCE paper by Bellare, Hoang, and Keelveedhi. And the starting point of their definition is classical PRF security. So which, like you see the representation in this picture over here. So you have a distinguisher here that is trying to distinguish whether it's talking to the real oracle, so where queries are answered with hash function evaluations, or an ideal oracle where it just gets consistent random stuff. Now, PRF security is very useful, but it doesn't quite map to the applications of hash functions, because usually, like in hash functions, the hash key is made public, whereas in PRF security, it's kept secret, right? So you might say, let's try and modify this game and give the hash key generated here to the distinguisher. But this is broken right away, right? Because the distinguisher could simply like query an X and get an answer Y. And then since he knows the hash key, he can do this check. And this check will never go through in the ideal world. Sorry, it will always go through in the real world and almost never go through in the ideal world. So this is a good distinguisher. But this doesn't work. Now notice that what makes this attack work is that the distinguisher at the same time knows the hash key and can query its oracle. And that way it can distinguish. So the insight of BHK was to split the adversary into two and to distribute these two capabilities among the two adversaries that originate. So you see this judge joker here that is supposed to be the distinguisher gets now split only in joker and only in judge, where the joker still plays the PRF game. So it gets access to one of the two oracles, but no hash key. And then it does its computation. It can pass some leakage onto the distinguisher, who gets the hash key, but no oracle. And with this information, it must decide. Okay. Now it turns out that also this notion is not achievable. This is too strong. The problem is, I can show you an attack here. So for example, the joker here queries, so this is called source, by the way. Source queries an x and gets y as an answer. And then it leaks xy to the distinguisher. Now the distinguisher knows the hash key and can just perform this check. And again, this check will always go through if the two are playing in the real world and almost never in the ideal world. Okay, so there's a number of ways out of this problem. The one that we are interested in is called statistical unpredictability. So what we do is we restrict, we do not consider like arbitrary PPT or unbounded sources, but we restrict the class of sources for which we require security. And the game the sources must satisfy is the so-called algebraic unpredictability game, is the game here on the right. So what happens here is the source plays in the ideal world, makes some queries, gets answers, then produces some leakage. And the requirement is that no even unbounded predictor can, given this leakage, can guess any of the queries made. So the queries in some sense must be high entropy. And you see, for example, that this prevents this attack from happening because here the source encodes the query in the leakage. So a predictor could just like look at the leakage and say, yeah, you queried X. Okay. Good. Now, this is the UCE notion for hash functions, and I won't be going into any detail here, but if you read this paper, the authors here show that this notion avoids the uninstantiability result and can be used to replace the random oracle across a number of interesting applications. Now, if you write down the sentence that I just said as a table like this, you might see the beginnings of a research agenda here somehow, because like the random oracle model is not the only idealized model we use in cryptography. There's many more. Here's a limited selection. And of course, like for each of these models, now you could wonder, well, just like UCEs is a good standard counterpart for random oracles, what is a good standard counterpart for each and every one of these other idealized models? Let me very quickly tell you about prior work. So we've already seen this question has been studied successful for the random oracle model. It has also been studied for the random permutation model a few years later. What we do in our paper is we add to this state of affairs and we study this arrow here. So this is the object of our paper. A bit more explicitly, what we do is we study a security notion for concrete groups, which does not fall under impossibility results, on the classical impossibility results, but allows you to instantiate a generic group in many interesting applications. Okay, let me show you how we did this. So our starting point is, you might recognize this. This is the UCE game that we saw just before. Let me walk you through how we modified this game to obtain a notion for groups. So of course, the first modification is here on top. You see, like earlier we had we generate hash function parameters. Well, of course, now it's going to be group parameters. Now, interestingly here, what happens here is more interesting. So the sampling of the hash key in the setting of groups is a re-randomization of the group of the given group generator. So you see, like earlier, we sampled the hash key. What we do now is we sample an exponent and we re-randomize the generator with that exponent. And now hash function evaluations in the real world become just group exponentiations with respect to this unknown random group generator. And of course, like now in the ideal world, what is the ideal counterpart to group exponentiations? It's just a random injection from ZP to the set underlying the group. So this is what we offer in the ideal world. Okay. So this is the notion that we end up with. The question now is, what is the right notion of unpredictability? Remember, also for UCEs, this is not satisfied unconditionally. You need to put some restriction on sources. Of course, like the same restrictions apply. If the source is not unpredictable, you can mount a similar attack than what you did for UCE sources. The main thing about groups is that this is not enough. So just considering unpredictable sources still gives rise to attacks. And let me show you one example. So suppose that your source queries picks x1 and x2 at random. It queries x1, x2, and x1 plus x2. It gets as reply h1, h2, and h. Now, in the real world, what will happen is that h1 multiplied with h2 is always h. This is just, associative property in a group. And in the ideal world, since you have like a random injection, this will almost never happen. Okay, so the source can basically do this check. This check will always go through here, almost never go through here, so it can leak just one bit. And of course, given one bit, like these three queries are very unpredictable. So this would be an unpredictable source that breaks the notion for groups. The reason being, of course, that with a group, you have an underlying group operations that we didn't have for hash functions and permutations. And you have this homomorphic property that a hash function does not satisfy. So our way out of this was to require a stronger notion of unpredictability, which we called algebraic unpredictability. And the game is here on the right. So it looks very similar to standard UCE unpredictability. But now the predictor wins not only if it guesses one of the queries, but if it guesses a linear combination of the queries. So for example, if you go back here, you see a predictor here could just say the first query plus the second query is the third query, because they are in a linear relation. And so if you require algebraic unpredictability, this source cannot be considered. So in a way, we have defined the problem away by restricting the class of sources that we consider. And now it turns out that this is still not enough. There are still attacks that arise. I can tell you that, so when we did this project for quite some time, we were happy with this, and we thought that we had captured all trivial attacks. And only a few months into the project, we realized that there are still attacks to be, yeah, go ahead.
I didn't get the counterexample.
Here, yeah.
There's a leakage that is one bit, so what does the distinguisher do then?
It just returns the bit. It doesn't. The source computes this. So again, source queries x1, x2, x1 plus x2. It gets back as answers h1, h2, and h. It locally does this computation. So is h1 times h2, is it h? Leaks the corresponding bit, and the distinguisher, and the distinguisher then looks at the bit and just returns it again. Okay. And again, so this is ruled out by algebraic unpredictability, right? Because they are in a linear relation. So as I mentioned, unfortunately, this takes not care of all the attacks. Let me give you an example. So now suppose you do the following. You sample a random x, and you query x and x squared. You get back h1 and h2. Then what the source can do is raise h1 to the power of x, because it knows x, and check if it's equal to h2. And again, just pass the leakage, this one bit of leakage to the distinguisher who returns it. And again, these like this source and this distinguisher, they will almost certainly win the game. So our way out of this was to impose a syntactic restriction on the source. So what we require is that sources are non-adaptive. So they, in some sense, they declare all the queries they want to make before seeing any answers. And then they have only very limited post-processing. Especially what we allow is a single group operation on the outputs. Okay, so this is the PGG notion that we end up with. Now, whenever you give a definition like this, there's two things that you need to worry about. First one is, does the notion suffer from trivial flaws, which is usually exposed by an analysis in an idealized model? And the second thing is, well, does it actually yield something interesting, or have we just given a definition for nothing? Okay, so as to the soundness of the definition, what we do is we prove that the generic group satisfies this notion. The proof is rather technical, so I can't go into too many details, but I want to highlight two things. So first thing is, in our formalization, sources are unbounded. So this allows us to capture a wider class of adversaries and also pre-processing attacks. The way that we formalize this in the generic group model is that we don't give the generic group oracle as an oracle, but we give it in full. So like the source gets the full generic group encoding, not only as an oracle. And of course, this is a stronger modeling of the problem. So it is interesting, but it is more technically challenging. And like the right tool to address the additional challenges that come up with is the bit fixing framework by Corretti-Dodis and Guo, which allows one to handle, among other things, exactly situations like this. The second point that I would like to tell you about is that our proof is somewhat different to standard generic group model proofs. What one usually does in generic group model proofs is one appeals to a theorem in mathematics called the Schwartz-Zippel lemma to ensure a consistent lazy sampling of group elements. But this only works if the sources are somehow polynomially induced, which is not the case for us. So these are arbitrary sources subject to the restrictions that I said before. And it turns out that algebraic unpredictability is just the right substitute for the Schwartz-Zippel lemma. So in some sense, we reinterpret the Schwartz-Zippel lemma, which is a theorem for polynomial sources, as an assumption that you make on sources, so that a similar proof strategy somehow works. Okay. Let me quickly give you an overview of the applications that we achieve. So first thing is we indeed show that pseudo-generic groups are a generalization of an Uber assumption of the Uber assumption, meaning that the Uber assumption holds in pseudo-generic groups. Also, generalizations of the Uber assumption, generalizations of the Uber assumption hold in PGGs. These have already been used before, for example, in this work by Canetti. We also show that, We also show that other applications fall under PGGs, which do not seem to be captured by the Uber assumption. So for example, we managed to construct UCEs for a restricted class of sources, which we call simple split. And this in particular, this means that we recover under PGGs all the applications that BHK show in their paper for this class of UCEs. And we also show that practical crypto systems, namely minor tweaks of El-Gamal, achieve security in strong security models, specifically forms of KDM, deterministic encryption, and RKA security. And as a corollary of our GGM result, we can prove that all these applications are secure in the GGM against pre-processing attackers. So we get this like modular way of proving things. Now, the applications that you see highlighted here in orange, in one way or another, use a hash function. And well, if you go through the proof, the reduction to PGGs queries hash function evaluations to the PGG oracle. The problem is that the applications that we want to prove only ensure simply unpredictable inputs. And so in some sense, what we do is we use the hash function as a bridge between simple unpredictability and algebraic unpredictability. And so we formalize this requirement as a new assumption on a hash function, which we call linear dependence destroyer, or LDD. The corresponding game looks a bit like this. So a source returns a tuple of hash inputs x. It doesn't see the hash key. And the adversary then gets to see the hash key and must return a linear combination, like the weights in a linear combination of the hash function evaluations. And the requirement on the hash function is that this holds for all unpredictable sources S and all PPT adversaries A. We have tried to build these. We have succeeded only up to a certain point. So what we show is we provide an instantiation of such an LDD for a class of sources, which we call low degree, which essentially return, the outputs they return are polynomial evaluations. So again, here we can use the Schwartz-Zippel lemma. And then we show via a compression argument that a random function satisfies this notion in certain parameter ranges. Okay, so to conclude, what happens in the paper is we provide a new definitional framework for assumptions on groups. Our assumption can both be seen as a translation of the UCE assumption to the context of groups, or as a generalization of the Uber assumption. We show that the definition we come up with is void of trivial attacks. This is the GGM proof. And then we show that some interesting applications follow from this notion. As for open questions, there's many. So for starters, the one that I would be very much interested in is improving the adaptivity of our notion. You remember that we had to restrict the sources to be non-adaptive to avoid one of the attacks. Can we somehow subsume this under an even stricter notion of algebraic unpredictability so that we recover at least some form of adaptivity? The notion that we ended up with is inherently random generators. So you remember in the definition of the game, we re-randomize the generator and then offer exponentiation with respect to this random generator as the PGG oracle. Can we do something about fixed generator? Can we instantiate PGGs under some plausible assumption? As for LDDs, do these exist for all statistically unpredictable sources? So not just low degree sources, but can we come up with a construction that actually satisfies this notion for all statistically unpredictable sources? And finally, and this is more of like a meta question, how far can we push this high entropy approach to instantiating idealized models and to connecting the standard model to a given any given idealized models? For example, here one question that maybe would be interesting is, can we say something? Let's say a scheme uses a group and a hash function, and we proved it's secure in the generic group in a combination of a generic group and a random oracle model. Is the combination of PGG and UCE the right notion to instantiate this? Yeah. The grad student says, thank you. Thank you all for your attention. I'm happy to take questions.
Okay, are there questions from you? I think there was a question. So let's start on the second one. Why is it important to construct PGGs for fixed generators?
Because it is a more powerful assumption. So it would give even more applications. There are, give me a moment, fixed generator applications in constructions of point function obfuscation. So you could actually try to, like, if you had a PGG for a fixed generator, you could try to instantiate those constructions. Those inherently don't work with random generator.
You mentioned, actually, I think I mentioned about this before, and you mentioned the generic group model design that you call group, the flag. This
yes.
Instantiability or something?
No, like this, okay. What is the meaning of a proof in an idealized model? One usually says that it shows that the construction is void of trivial attacks, those that you could replicate even in the presence of an idealized primitive. This is what we show. A stronger result that one could prove is try to instantiate this under plausible but arguably very strong assumptions. So, for example, some form of obfuscation. One could try to build a PGG, and then if you believe in obfuscation, then you have constructed a PGG. But that's stronger, right? Yeah.
Okay, then. And to instantiate a group function, let's say, so which relies on a group, we need to, well, say which groups are weak and which groups will provide enough obfuscation and entropy. How do you tell ones from others?
Well, to some extent, we are already doing this, right? When we use a scheme that has a security proof in the generic group model, we usually instantiate this with, one says, an appropriate elliptic curve. This is something that is known to be false, right? Because we know that, like, generic groups do not exist, just as random oracles do not exist. And then I would say, like, if you were still fine doing this with generic groups, you might very well be fine doing that with PGGs. The only difference is that you knew this to be false for generic groups. Like, no concrete group is a generic group. But you might, at some point, we might end up in a position where we can prove that a given group is a PGG. Like, this is the, if you want, philosophically, the main difference.